Hello and welcome to Learn Rust. I'm Reese, and in the last video we learned about variables, mutability, and comments. In this video we're learning about data types. Data types are sometimes referred to as primitives. As the Rust book states, every value in Rust is of a certain data type, which tells Rust what kind of data is being specified so it knows how to work with that data. There are two subsets of data types, scalar and compound. In this video, we're focused only on scalar types. These are types of a single value. Of those, there are four primary kinds of scalar types. Those include integers, floating point numbers, Booleans, and characters. Now, you should be aware that all of this data can be represented in memory addresses. These memory addresses are often virtual, but somewhere down the line there will be physical addresses. In other words, there is no virtual without physical. And by physical, I mean tangible, electronically manipulated rows of cells that are either considered to be off or on relative to some threshold. An electrical current may have to be sustained to retain this memory, but for some kinds of memory this isn't needed. Since we have different kinds of memory that can be produced at varying costs, economics enters the picture and affects which memory we choose to put in our PCs, video game consoles, server farms, etc. For now, we're just focused on the memory address. Since each cell in a memory address can either be one value or another, generally represented as 0 or 1, I'm actually referring to binary. A single digit in binary is called a bit. Binary is a base 2 numeral system. 8-bit, for instance, literally means there are 8 bits. These could be 8 cells in a memory address. The same goes for memory addresses that are 32-bit, 64-bit, and so on. It turns out it's possible to represent the data types I mentioned as binary in memory addresses. First, let's look at integers, which are numbers lacking a fractional component. While this is not a computer architecture or math course, you should know that there are 2 to the power of n possible integers that a single memory address can store as binary. N, in this case, is simply the number of bits in the address. Therefore, if you have a 32-bit address, it can represent 4,294,967,296 different integers. It's common in programming languages to support 2 kinds of integers, unsigned and signed. An unsigned integer has no sign, meaning it cannot be negative, whereas a signed integer can be negative. Since unsigned includes 0, if you subtract 1 from that big number I mentioned, then that's the maximum 32-bit unsigned integer value in Rust. For signed integers, negative and positive occupy approximately 2 respective halves of all possible n-bit values. I say approximately because we can't forget 0. This is achieved through the 2's complement representation, which you can read more about on your own. Anyway, this table found in the Rust book shows us the possible integer scalar types. Usually, you'd want to use an i32 because operations performed with it tend to be faster than the others. This is true of other programming languages as well, so the i32, by the way, is the default data type for an integer literal in Rust. A literal, by the way, is a fixed value. As for isize and usize, let's say you use one or both of them in a program. If that program is running on a computer with 64-bit architecture, then they would use 64 bits. They depend on the architecture. Let's look at another table in the Rust book. We can represent integers in different literal representations. Most programmers use decimals in most circumstances. In Rust, you can add underscores to decimal values to make them easier to read. For instance, this underscore here helps us read this as 98,222. We can also write integers in hexadecimal, octal, binary, and as bytes. A byte, by the way, is 8 bits. Some of these literals may appear alien to you, but actually there are situations where it's easier for us to reason about our code using alternative literal representations from decimal. This will, no doubt, come up later for you if it hasn't already. You might be wondering what happens if you add beyond the allowable range for an n-bit integer. Let's look at an example. You'll notice that one way I can explicitly define types is by specifying the data type after the number. In this case, we're using unsigned 8-bit integers. Their range spans from 0 to 255. Here, I'm adding 1 in 8 bits to 255 in 8 bits. If we try to compile and execute this code, we get an error, specifically an arithmetic overflow error. This is because we're exceeding the maximum allowable range for the data type. You might be wondering, why not just wrap around to 0? Well, that's one way to deal with this problem, as long as it makes sense for your program. We can instead use the built-in, or rather intrinsic, wrapping method like so. And when I say method, I'm referring to a term in programming. A method is slightly different from a function, but seeing as we haven't covered functions yet, you'll just have to trust me. For now, just know that the wrapping underscore add method assumes that the literal you supply to it within these parentheses here should be of the same data type as the literal on the left-hand side. So actually we can get rid of this U8 here on the right-hand side. Let's save this code. And now I'm going to compile and execute it again. And as you can see, the value of x is 0 because the wrapping add method worked. It wrapped around to 0. Anyway, you can read more about overflows and how to handle them in the Rust book, upon which this entire series is based. To introduce floating point numbers, I will first address inference. If it isn't already clear, Rust can infer types. The upper let statement here, assigning x 2.0, will infer that x actually has a data type of F64, a float 64. That is because the F64 is the default data type for floating point numbers in Rust. It turns out it's just about as performant to use an F64 as an F32 on modern CPUs, except an F64 has much higher precision. In spite of that, the lower let statement explicitly defines an F32, going against the default. Furthermore, you should be aware that Rust represents floating point numbers in memory according to the IEEE 754 standard. Since this standard encodes exponents into memory addresses, it can represent truly mind-boggling numbers. You can read more about this standard on your own time. Rust supports all the arithmetic operations you've come to love and depend on, including addition, which we've already covered, subtraction, multiplication, division, and finding the remainder. You'll get accustomed to these and other operators as you proceed along your Rust journey. There is, of course, a Boolean type which can either be true or false. If you don't know, Boolean is referring to its namesake, who happens to be George Boole. In 1847, He published a pamphlet called the Mathematical Analysis of Logic, laying the modern foundation for what would become known as Boolean algebra. He was a pioneer of algebraic logic, along with contemporaries such as Augustus de Morgan. You may even synthesize de Morgan's laws while programming without even knowing it, but that's a topic for another time. Finally, we've reached the last scalar type of this video, the character type. Remember how we supplied a string literal to the printline macro? Well, the atom, or rather atomic unit of the string, is the character. A string is denoted with double quotes, whereas a single character is denoted with single quotes, as you can see here. And yes, emoji are valid characters. Why not? Rust's character type is 4 bytes. That's 32 bits. There is plenty of room for the characters which compose our natural languages, such as Chinese. How? Well, Rust adheres to the Unicode transform format 8. We often shorten that to UTF-8. Read more about it if you want. We've now made our acquaintance with scalar types. In the next video, we'll study compound types. These are types which can group scalar types. I hope you join me, and don't forget to like and subscribe.